So here we're asked to evaluate this surface integral. We're given the vector field and we're told what the surface looks like, and we're given the corner points of the surface. Let's take a look at that. So the problem is talking about the piece of the plane that has vertices on the x-axis at 1, y-axis at 1, and z-axis at 1. And they're implying that we should use Stokes' theorem for this. Now, I think it'd be worthwhile to do it both ways and kind of see which do we like better. The fact that it's 3 different lines means that if we do it as a line integral, we'll have to do 3. Now those 3 may be easier to do than the one that we would do straight from the surface integral. So let's do the surface integral, see what it would look like, and then we'll do the Stokes' theorem with the 3 lines and see which one we like best. So since our vector field is z squared, y squared, and x, we'll find the curl of that. And I happen to have that on my calculator here. So there's the vector field. I've stored it in F. Here I have a program that I shared with you called curl. And we want to do the curl on the vector field F that we just entered. And so you can see there's what it comes out to. Now, since this is a plane with x-intercept 1, y-intercept 1, and z-intercept 1, I know that the equation of this plane would be an x plus y plus z equals 1. Which means I also know that a normal vector for this plane would be at 1, 1, and 1. So, if that's the normal vector, then we can do the dot product of these two, and that would be 0 times 1, 2z minus 1 times 1, and 0 times 1, all added together, which would just be a 2z minus 1. And so we need to integrate that over a region, that region being what we get when we look at the projection of this surface onto the xy plane. So here's my xy plane. I see here that the x-intercept is a 1, the y-intercept is a 1, and it's the region between there and the origin. So the line here would give us this region. Now that line would be 1 minus x. So we can find the area of this region by integrating first with respect to y, 0 to 1 minus x, and then with respect to x from 0 to 1. Well, now since we have x's and y's, we need to convert our z into x's and y's. Well, over here we had x plus y plus z equals 1, which means z would be 1 minus x minus y. So this integral then would be a 2, 1 minus x minus y minus 1 dy dx, or 1 minus 2x minus 2y. again, I'll type that onto my calculator. So, as you can see, that comes out to be a negative 1/6. So that wasn't hard to do just by evaluating the surface integral, especially with the help of our TI calculator. Now, to use Stokes' theorem, we would have to find each of those three lines and do the integral along the lines. So let's see what that would look like. I'll erase this and we'll try a different one. Now, when they say counterclockwise orientation, we'll assume that they mean as viewed from above, so kind of like what we're looking at it right now. So let's start by going from the point 1, 0, 0 to the point 0, 1, 0. So from the point 1, 0, 0 to the point 0, 1, 0 means that we would have a parameterization our curve would be what? We would want to say 1 plus 0 minus 1, so that would be 1 minus t for x, 0, and then 1 minus 0 would be just t, and then z would be a 0. So there would be the parameterization for this first curve. Now we would want to do our integral over this curve of f dot dr. Now I'm going to kind of cheat a little bit, well, maybe a whole lot, and do my TI 89 program that I shared with you called f dot dr. And so here's the f that we had earlier, here's the r. We can just give those two quantities to our function f dot dr, and it'll give us this integrand. So my TI 89 gives me the f dot dr to be a t squared. And now we want to do the integral of t squared dt 0 to 1. That comes out to be 1/3. So now let's go along this line. From, what would that be, 0, 1, 0 to 0, 0, 1, and that we could parameterize with 0, x is not changing, 1 minus t, and t. And so this one the f dot dr, I'll just do it on my calculator, just try it on yours. I've already shown you the program and how it works. It comes out to be a negative of t minus 1 squared. Now again, that's just straight off of the calculator. We integrate that. And then we want to go on the final line from 0, 0, 1 to 1, 0, 0. And that completes our region. And the parameterization, much like what we did on the other two, would be a t0 and 1 minus t. And so this integral, the f dot dr would be t squared minus 3t plus 1. We integrate that with respect to t, and we get negative 1/6. So if we add these up, 1/3, negative 1/3, and negative 1/6, we get negative 1/6. Same thing we got when we did it from the definition.